Here's to anyone who's ever looked up. The airheads. And the space cases.
Live long and prosper.
The flight fanatics. The armchair astronauts. And the casually curious. Here's to those who know the thrust in newtons of a Pratt & Whitney J75 turbojet engine. And those who silently ask, what's keeping this thing in the air? Here's to those who can list the name, mission history, and favorite breakfast of every Mercury astronaut. And those who've ever searched for, how does a toilet work in space? Here's to the people who know a P-38 Lightning from a P-51 Mustang. And the people who thought those were the names of cars. Those captivated by the miracle of flight. And those who are just happy to make their flight. So whatever captures your curiosity.
We choose to go to the moon.
Or propels you to new heights. When it comes to the sky, there's space for all of us.
Good evening, and welcome once again to the 2024 Exploring Space Lecture Series, sponsored by Aerojet Rocketdyne and United Launch Alliance. I'm Matt Schindel, Curator of Earth and Planetary Sciences here at the Smithsonian's National Air and Space Museum. This year, all four of our speakers will be talking about sample return missions. Last month, we heard about what the samples returned from the moon have taught us about the history of our solar system and how they're helping us to plan for future missions to send humans back to the moon. Our next three speakers will talk about exciting robotic missions to bring home pieces of comets and asteroids, as well as what we aim to learn when we can bring samples home from Mars. NASA's Stardust spacecraft launched in 1999 on its mission to collect dust samples from the coma of Comet Wild-2, along with samples of interstellar dust passing through our solar system, and return them to Earth for analysis. It was the fourth mission launched under NASA's Discovery program, which continues today to use science missions with small price tags, relatively small price tags, to address big questions in planetary science. When the sample return capsule landed in Utah in 2006, it became the first successful mission to bring back samples from beyond the Earth-Moon system. NASA repeated this feat only very recently with the OSIRIS-REx mission that returned samples from an asteroid using the technology that Stardust pioneered. The museum proudly displays the Stardust return capsule in our Exploring the Planets gallery, where it shows very noticeable scorch marks, the telltale signs of return through Earth's atmosphere. And if you haven't seen it yet, I encourage you to go and take a look at it tonight or the next time you're in the museum. Our speaker tonight, Dr. Scott Sandford, is a research scientist at NASA's Ames Research Center, where he leads the center's astrochemistry and astrophysics laboratory. Dr. Sandford was a co-investigator on the Stardust mission and led part of the effort to analyze the returned samples. He has since served as a co-investigator on the joint Japanese-U.S. Hayabusa mission that brought back samples of asteroid Itokawa to Earth in June 2010. And he's currently a co-investigator on NASA's OSIRIS-REx mission, which returned samples of asteroid Bennu to Earth last year. And in recognition of all of this work on extraterrestrial materials, he has had an asteroid named for him in 2004. So as Dr. Sandford will tell us, what scientists found in the returned comet samples surprised them and gave them an unexpected clue about the solar system's early development. Rather than give away that surprise, I'll go ahead and hand things over to Dr. Sandford so he can present his talk, the Stardust Discovery Mission, bringing Comet Wild-2 samples home to Earth. It's my pleasure to present Dr. Scott Sandford.
I've been told to use this microphone instead, so can everybody hear me all right? Looks like, okay, I'm seeing hands. Well, thank you very much for having me here. I'm always happy to talk about the Stardust mission. It's the sample return mission that I sort of broke my teeth on, and it'll always be near and dear to my heart. And I do encourage you to go up and look at the capsule if you get a chance. I visit it every time I'm here. It's an old friend now. I really encourage you to get up there and see it. So I said I was going to talk about the Stardust mission, but before I do, I would like to take a few slides to talk about why we do something like this. Why do we want samples brought back instead of just going to a place and observing it? And then why do we want to go, in particular, to a comet? So I'm going to have a few slides I'll talk to that about. See if we can, there we go. Okay, so here's an artist's rendering of the spacecraft. I'll talk about some of the components of it later. And then on the right is a picture, it's actually two pictures superimposed of the comet we went to called Wild-2. One image was taken with a low exposure so you could see the surface of the comet, and then the one was taken so that it was overexposed, and it shows all the jets of dust and gas that were coming off. And we took advantage of that outgassing by flying through the coma, so we didn't land on the comet, we didn't run into the comet. We flew through the cloud around it and collected a sample of that and brought it back. Whoops, got to keep my buttons straight here. So why are we interested particularly in comets? Well, our solar system was made from material in a dense interstellar molecular cloud. And the word dense I put in quotes because if you made the best vacuum you could in your laboratory on Earth and exported it to space, you'd make a dense cloud. So it's still pretty thin, but it's dense compared to the rest of space. And a collapse of a portion of one of these clouds formed a disk with a central protostar. On the right, you can sort of see a schematic of that. And in this disk, the temperatures varied depending on how close you were to the forming sun. So things very in close got hot, but things further out stayed relatively cold. And we think comets formed out in that cold region of the solar nebula, where probably the temperatures didn't get so hot that they vaporized everything and changed whatever the original material that had gone into the disk was. So most of the material in the disk is swallowed into the forming star, our sun, or it's ejected from the entire planetary system, but small amounts hung around and made the planets, and even smaller amounts hung around to make asteroids and comets. And so if you really want to study what that original material was, what everything else was made from to begin with, you don't want to go to a planet. You want to go to small bodies. I don't have anything against planets. I mean, the Earth is a great place to set down your potato chips and beer when you need to change a channel. But if you want to know what the raw material of the solar system was, you can't use a planet because all the material on the planet has been altered. It's been melted, it's been subducted under the ocean, it's been paved over by your local highway commission, it's been plowed under by farmers and so on. And so it's just not a good material to go back to the beginning of the solar system. But smaller bodies like comets and asteroids have undergone far less of that kind of processing. Comets, have not melted. They don't have highway commissions on them. And so material on those has been preserved much better. And we do get samples from these objects for free. They come to the Earth as in the form of meteorites and small dust grains. So in the middle pictures on this slide, you can see in the bottom a NASA high-altitude aircraft, which we have used to fly in the stratosphere to collect cosmic dust that's settling down from outer space. This is what I did my thesis work on. And then on the right image, you can see someone, a colleague of mine, on one of our trips down to Antarctica to collect meteorites. These are all materials that land on the Earth for free, and we have studied them and learned a lot about the origin of our solar system. But the problem is all these samples are orphans. We don't know where they came from. We can't even necessarily tell whether a particular object came from a comet or an asteroid, much less which comet or asteroid. So this is where going to get the sample can be an advantage. Also, we think these small bodies, like comets and asteroids, may have played a key role in getting life started on the Earth because they would have incorporated within them organic compounds made in the protosolar nebula and even before in the interstellar dense cloud. And these would have been delivered to the surfaces of the forming planets and would have been available to help get life started. And so we think the organics in these small objects are of intense interest. Okay. Try again. Okay, now why sample return missions? NASA mostly is known for missions where you send a mission out to a place and you make measurements. And that's an excellent way to learn a lot about a system and particularly about the system's behavior. But there are some things you can't learn that way. If you're an astronomer on a mountain peak and you spot an astronomer on another mountain peak, you can study each other through your telescopes, and you may figure out when you each eat lunch and what your favorite colored shirt is, but you're never going to know that each other's DNA, each other's biochemistry is based on DNA. To do that, you have to cross that gulf between your mountains and stick a needle in the other guy. So sample return missions allow you to bring a sample back to the Earth and study it in ways you can't do on a spacecraft. Spacecraft are associated with very specific limitations with cost, power, mass, and reliability. Whereas if you bring the sample back here, you can study the sample using equipment that's here on the Earth. You don't have to launch it. And so this allows you to use instruments to study the sample that you would never get to the body itself. So for example, one of the instruments I've used to study the Stardust samples was the Advanced Light Source in Berkeley, California, where the instrument is bigger than the launch pad Stardust left from, much less the spacecraft. So this allows you to use state-of-the-art analytical techniques on the Earth, and you don't have to worry about getting them up into space. And then also, since the samples here on the Earth, you can do these analyses iteratively and fully adaptive. If you're going to send an instrument to a planet, you have to decide ahead of time what instrument that should be, and maybe you all get together and decide, well, we need to measure the value of the parameter A. And you get there and you measure parameter A, and the main thing that the value of parameter A tells you is that you should have measured parameter B. So now you've got to make another spacecraft if you want to do that. But if you have a sample in your lab and you measure A and it says you should measure B, then no big problem. Go down the hall to the B measuring machine and get on with it. And also, since the sample is here, you can have multiple groups studying it. They can compare their results, they can discuss, or in some cases argue about the results, and that this all helps further your understanding of the samples. And then the last thing I really want to stress, particularly for anybody who's younger in the audience, is when the return samples come back, we don't study them and say, oh, that was interesting, and then throw them out. They're all instead saved in a curatorial facility that keeps them pure and pristine, and they're available to people to request to study in the future. And I'm sure the speaker last month who talked about the Apollo program must have mentioned that people are still studying rocks all these decades later from the moon and learning things from them. And the Stardust samples I'll be talking about are the same thing. They'll be getting studied for decades to come. And so they're a resource that subsequent generations can take advantage of. So basically, when you do a sample return mission, your mission's payload includes all the world's analytical instrumentation and pretty much all the world's analysts, including ones that aren't born yet. Okay, here's just a quick picture of the spacecraft before it launched. I'll talk a little bit more about the hardware on it, but not a whole lot. And then again, there's a picture of Wild-2 again, just to show you what it looked like when we flew by it on January 2nd in 2004. Okay, having a hard time to get it to go here. Okay, so why did we go to Wild-2 of all comets? Well, partly because we could get there. It turned out Wild-2 was very accommodating for us. In its ancient history, it would have been in orbit out around the sun, way far out in the solar system. But at some point, something nudged it into the inner solar system, and it had an encounter with Jupiter, which on this map is the second smallest little ring in the middle. It's labeled with Jupiter's orbit. It had an encounter with Jupiter, which torqued its orbit so that now it was in an orbit where the furthest it gets out is out into the outer solar system, but not way out. And the closest it got was Jupiter. But in 1974, it had another encounter with Jupiter, and it got torqued into the orbit that you see in red there. And now the orbit is the farthest it gets from the sun is Jupiter, and the closest it gets to the sun is almost down to Earth. So this suddenly brought the comet to us. And so that made it a lot easier to get there. And that played a large role in our picking Wild-2 as a target, because we could get there cheaply. But even if we could get there cheaply, it wasn't all that easy still. So in the new chart on the right here, you can see Wild's orbit is in red, and the sun is the dot in the middle, and you can see the Earth's orbit is yellow. So we launched into an orbit that's that inner green oval, and went all the way around the sun and came back and met the Earth again to do an Earth gravity assist. And that gave us a boost that flung us into the outer green ellipse, and that ellipse crosses the comet's orbit. So that's great, but when we got to the comet's orbit, the comet wasn't there yet. It was still out in the other part of the solar system. So we had to go around the sun a second time, and then the third time we came out, we met the comet. And then we got our sample, and then we went back and dropped off the sample at the Earth. So this total orbital trajectory of going around the sun 3 times, meaning we travel a total distance of about 2.88 billion miles. So if you divide that into the cost of the mission, that's about 7 cents a mile, which is pretty good. It costs more than that to send me as a NASA employee to places, so that's quite a deal in a way. And I'll point out that even though we traveled all these miles, ultimately is what we did is we took off from Florida and we landed in Utah. So, to be honest, there are easier ways to get from Florida to Utah. Here's one way I found on MapQuest. So even though we traveled all that distance and we did so at very high velocities, our actual Stardust actual average terrestrial velocity, I think, was about, if I did the math right, 0.04 miles per hour. So you could have watched the launch in Florida and crawled on your hands and knees to Utah and had plenty of time to sightsee along the way and still gotten there in time to watch the landing. So, but the difference is the Stardust spacecraft saw things that you would not see crawling on your hands and knees across the United States. So. Okay, whoops, I went 2. There we go. Okay, so I'm not going to talk about the spacecraft a whole lot, but one of the things I do want to point out is that we flew by the comet and collected our sample on the go, and we passed the comet going 6.12 kilometers per second. So that's something I think like Mach 20. So I don't know if you've ever actually personally run into something going Mach 20, but I'll bet it stings, okay? And so one of our real concerns was when we flew by the comet, if we ran into anything very big, we could destroy the spacecraft by being basically hit by a cannon shell. So the leading edges of the spacecraft all had something we call Whipple shields. So these are layers of plates of metal and Nextel, which is kind of a material like you use in bulletproof vests, on the leading edges, so that grains up to about 1 centimeter that hit us would be shattered and broken into pieces, and as they plowed their way through these various layers, ultimately stopped so that the spacecraft would be safe. And very few things on the spacecraft peeked around these shields. The camera did through a periscope, and the collector, which you see labeled at the top here, the aerogel collector, was designed so that at the critical moment it could pop up into the stream of dust we were flying through and then be retracted. I'll talk about that a little bit more in the subsequent slides. Okay, so now, how do we collect something if we are going Mach 20? I mean, if you try to catch a softball going Mach 20, it's just going to blow a hole through your glove. So how did we collect this dust? Well, we used something called aerogel, which is the world's lowest density solid. And I know it is because the Guinness Book of World Records says so. And it is basically extremely fluffy glass. And you see the structure of it through an electron microscope on the left here. I actually have a piece of aerogel here. Let's see if I can show it to you. I'm going to set down the mic here for a moment. Phone as best I can. So aerogel is almost perfectly transparent, and the best way to see it is to shine a laser through it so that you get scattered light off of it. So here is my laser shooting through this box where there's no aerogel. It's almost invisible. And then here I'm shooting through the aerogel. I don't know if you can see because I'm in a bright light, but maybe you see the red beam. So aerogel is very hard stuff to work with because it's so almost invisible. The first piece I ever got to test for this mission, I broke a piece off and lost it, and it's because it stuck to my eyebrow. And it was there all day and nobody noticed, including me, until I went home. And then I was trying to put my glasses back on and they wouldn't go because there was something in the way, and it was aerogel. But aerogel is really fluffy, and this allows us to collect dust at hypervelocities. So how does this work? Actually, I think most of you would have a fairly good intuitive sense of this. If you fire a particle at this velocity into a plate of metal, you get what happens is what you see in the lower right here. The particle stops on a dime in the metal, there's an explosion, most of the material vaporizes, and you have this little crater, which may or may not contain a little bit of your original projectile in it. But if you fire a particle into aerogel, it's kind of like firing a BB into styrofoam. It doesn't have to stop on a dime, it punches its way in. And you can see in these pictures on the upper right here that as the density of the aerogel goes down, the particle can penetrate deeper. And as it penetrates deeper, it takes longer to come to a halt, and therefore the process is less violent. And like I say, I think you all have an intuitive sense of this. If I told you we were going to do an experiment where I'm going to take you all outside and we're going to load you into 2 buses and we're going to get them out on the freeway and we're going to get them up to 60 miles an hour, I'll follow you in a car because I'm running the experiment, I get a car. And then I'm going to announce to you over the radio that in the interest of science, I've cut the brake lines on both buses. Okay, but it's okay, it's for science. And then I ask everybody on the buses, which would you rather do? I said, don't worry, I've arranged for you to all stop without brakes. One of the buses is going to stop by running into a brick wall, and the other is going to run into a pile of pillows. Okay, who wants to be on the pillow bus? Okay, I think you have an intuitive sense that slowing down more gradually is much less violent. And so that's basically what aerogel does for us. It gives us a less violent collision. Okay, so, whoops. So here's the capsule, the return capsule. This is the only part that came back to the Earth. The rest of the spacecraft stayed in space. And it's called a clamshell because the lid can open kind of like a clam, and then it can deploy this aerogel collector out of the top that peeked over our shields, and any dust hitting that aerogel, if it was small enough, would come to a stop. If it was big, it would have just blown its way through, but most of the dust was small and it stayed. And then once we had the collection, we folded everything back up, closed the clamshell, then returned to Earth, and we kicked this capsule loose and sent it into the atmosphere and then diverted the spacecraft to go back out in space. And then the capsule survived entry the same way a meteorite does, and the same way that, like the Apollo mission capsules did. You have an ablation shield on the front that ablates away. You burn off the outer part to save the inner part. And so you have a shield on the brown part on the right side image there, which has a certain thickness, and you enter the atmosphere and you just vaporize some of that away as you're slowing down, and you have this gigantic heat wave, and that burns some of that material away. So by the time you come to a slow enough speed you can pop a parachute out, that shield is thinner, but the inside is still safe. Okay, so I'm not going to talk a whole lot about the comet itself because I want to get to the samples, but we saw a lot of things in this comet that were kind of a surprise to us. You see the jets coming off from this double exposure. All those things that look like craters, those circular depressions, are not impact craters like they are in other things, because if you look at them carefully, you see they have flat bottoms and the edges are cliffs. All of these features you're seeing here are associated with the fact that ice on this comet is subliming and going away as a vapor. That's what gives you their comet tail. It blows dust out. And all these features are associated with the sublimation of this ice, not from impacts. And so we saw a lot of sort of geometries and geography that we just normally don't see on small objects. And in fact, I think the next picture allows us to compare Wild-2 on the left with some other objects on similar scales. So asteroids, you can see the craters there are more rounded. They have lips on the edges of the craters. None of this on Stardust images. And in fact, Stardust doesn't look like other comets we've imaged. It's got a lot more relief in it. And that's probably because these other comets have been around the sun hundreds of times, and they've lost a lot of their outer ices, and they've collapsed down into a more central core, whereas Stardust only started going by the sun close up in 1974, so it hasn't gone around the sun that many times. So we're seeing the early life of a comet in the inner solar system with Wild-2. Okay, so we knew almost right away when we flew by that we had captured dust, and that's because on the front of this, on the front of our shields, we had detectors that could measure things banging into us, and a lot of things banged into us. So on this plot on the right, the axis going horizontally is time, and at time 0 is the closest approach to the comet. The axis sort of pointing towards you in the audience is the size of the object that was hitting us, and the one pointing up is the number of things that hit us. And so you can see that as we got close to the comet, we were hit by lots of things, mostly small things, but some big things. And then later, for some unexpectedly, we ran into some more dust, which probably means the comet had shed a piece that we never even spotted. But we flew through some of the material that it released. So at the highest size scale there, we're looking at particles that actually would have quite possibly destroyed the spacecraft if we had not had the Whipple shield. So it was a good thing we had those. So anyways, we had this data after the flyby, so we knew we had collected particles. So that was a big relief. Okay, we came back to the Utah Test and Training Range. We came down to land in the dry lake beds of the Utah Test and Training Range. That's that brownish patch in the upper left of the picture of Utah there. Now, of course, dry lake bed is kind of an oxymoron. A lake is not dry. Dry is not a lake. But this is an area where sometimes it's dry and sometimes it's a lake. And we came in back in January, and at the time we came back, it was neither of those. It was a mud bath. But there are advantages to coming back there. It's highly instrumented airspace. There's flat terrain with very little vegetation, so it's hard to lose a spacecraft that lands. There's a lot of trained personnel around, and there's almost nothing to hit. That's an important one. NASA doesn't want us to hit things when we come back. But there are some disadvantages. One is, of course, that potential for standing water, which we didn't have to deal with. And also, since the military uses it for testing, there's sometimes unexploded ordnance around, which was one of the last nightmares I managed to shed is after the capsule landed and didn't blow up. Okay. So here's, on the left is a picture of the fireball of the capsule entering the atmosphere, and on the right I have an image. Let's go ahead and start that. There's a narrative with it, and I'll let them mostly talk for themselves. But you'll see the capsule start to appear just about in the middle of the frame.
5, 4, 3, 2, 1. Pleiades, rapid brightening.
So you can see the capsule right now is a little dot in the middle.
Sees it. Near spec is acquired.
So and we knew precisely to the second when it was going to come back, because if it was off that second, it would have either entered too shallow and bounced out or too steep and burned up. So we had to hit it just right.
Above Mars.
Okay, at some point you'll hear them talk about peak heating, and then you'll start to notice that this fireball starts to develop a trail, and that's the plasma of hot material burning. So you can see the tail now. And then just as a little bit of artistic, poetic circumstance, when this thing goes out of view behind the edge of the window on the right, if you look carefully, you'll actually see two natural meteors go across the sky.
Near spec has a great
we couldn't have timed that better if we tried. So yeah, there's one above and one below. See if I can spot them here. Well, yeah, there went one right there. I don't know if you saw it or not, but anyway.
HDTV, you got a strong wake. Go get.
Okay, so the capsule came down in the middle of a snowstorm, through a hole in the snowstorm, in the middle of the night, and in a fairly strong crosswind. So when it hit, it bounced up in the air while it was moving sideways, and it spun in the air, landed on its rim, and bounced again, landed on its rim again. And then once this last time on the rim, it rolled like when you roll a quarter on a desk, it rolled across the desert. You can see the track here a little bit. And eventually it laid down on its side, and it did a little death spiral and ended up on its side. And so you can see the final picture there. And if we can run this movie, I think maybe I can do it. Yeah. So this is some video I took of after we got to the capsule, and you can see right about now, you can see that track going off into the desert behind you. That's the roll marks from the spacecraft. So it traveled quite a distance on the ground before it finally came to a halt. But it didn't land in water, and so I was happy. Okay, so there's the capsule, returned safely to Earth. So after it returned, I took some gas samples from around the SRC because we wanted to know whether it was giving off any gases, because these were potential contaminants that we could find in our samples. And then the Lockheed personnel wrapped the whole thing up. We got it in a helicopter, got it to a temporary clean room in a nearby building, and the heat shield and the back shell were taken apart. The sample part was removed. Everything went into boxes that were purged with pure nitrogen, so we could keep everything as clean and pure as possible. And then we all got a few hours of sleep, and then see if I can do that. Then the next morning we loaded it onto a C-130 and flew it to Johnson Space Center, where it went into a dedicated clean room in the curatorial facility there. This is the same building where they keep the Apollo rocks and Antarctic meteorites. And we took the whole thing apart, and you can see in the lower right the principal investigator, Don Brownlee, giving the victory sign because we finally had spotted an impact in the aerogel. When we first opened it up, it looked so clean, we all kind of secretly had a thought that maybe they forgot to open it. But in fact, when we got it open and got it in good light, we saw that we did in fact have our particle impacts. And here's sort of what they look like. So on the lower left, we did have particles that ran into the frame that held the aerogel, and we got those craters, just like I talked about before. But particles that hit the aerogel punched long paths into the aerogel, just as we expected. So on the lower right photo shows a couple of 3 different tracks that went into aerogel. The one at the very top, which is the hardest one to see, is really thin, almost looks like a carrot, right? And that's what the kind of track you get when the particle that hits you is a nice solid like mineral grain or something like a BB, and it just punches this long thin path, and at the end of that path is your particle. But many of the tracks look like these two bigger ones at the bottom where you have this big bulbous thing and then lots of little roots come out of that. And that told us that a lot of the grains we collected were not individual grains, but were little aggregates of grains. They were little clusters of things. And then when they hit the aerogel, the cluster broke apart and all the different parts went in different directions. And the longest paths there are due to the largest particles within those aggregate grains. So here's just a close-up of one of those. You can see the bulbous area, the particle entered on the very far right there. And then you can see at the ends of these various tracks, little BBs that are the rocks that survive the whole entry process. Okay, so once we had the samples back, we had multiple teams ready to go to study these samples, which are very small, by the way. These are mostly so small you can't see them with your naked eye. So we had 175 scientists from institutions all around the world who studied these samples during a preliminary examination, and papers came out in a couple of issues in scientific journals. But as with all other collected extraterrestrial samples, the samples were, at the end of the mission, made available for the entire world's community of scientists to request for analyses. And so papers on these samples have continued to come out over time, even after the mission was all over. And this will go on for a long time. So I'm going to hit some highlights from what we learned from the samples, and don't get freaked out by the fact that there are some graphs and things. I'll hit the highlights and you won't have to worry about that much. But I just wanted to point out the progress in viewing comets. So on the left here you have a woodcut of Donati's comet made in 1858. That tail is probably tens of millions of miles long. I don't know what the resolution of a woodcut is, but it's probably not that high. And on the right, you see the interatomic spacing of atoms in a mineral grain taken from the comet. So this is an increase of a spatial resolution of at least a factor of 10 to the 15th. So that's, what is that, 1,000 million millions? Something like that. So one of the big surprises we found out is, I told you that we thought comets formed in the outer solar system, and so you might expect them to be made of the cold things that were out there that never got hot because they were not near the sun. But when we actually started looking at the samples, we found out they contained a little bit of everything, including minerals that only form in really hot environments, that they must have formed near the sun. And like in the lower right there, that vanadium titanium nitride mineral is like one of the first things that forms if you cool a superheated gas of solar composition down. So we had things that were high temperature, but we're living in a low temperature body. And also these things didn't really belong together. They wouldn't have formed in the same time in the same place. But they all got together in the comet somehow. So and then on top of that, you could also look at grains and find out that there were parts of the grains that were full of low temperature stuff. So and this is a picture of a grain that is a composite grain. So it has an iron sulfide lump, and then this MgSiO3 is a pyroxene, and then there's a bunch of stuff that's fine-grained, and it has a composition that's basically similar to the heavy elements in the sun. So that may be our primordial stuff. But down in a corner there, where it's protected by the iron sulfide when it entered the aerogel, is a blob of carbon. And this carbon is a low temperature material. It could not possibly have formed where these other minerals formed. And not only that, but this carbon has weird isotopes in it. The nitrogen in it is enriched in nitrogen-15, which suggests that this is carbon that actually probably existed before the solar system. So this may be carbon that's even older than the solar nebula. And in fact, we know we have some grains that are older than the solar nebula. Again, don't worry about the numbers and so on, but one of the things you can do with samples is look at their oxygen isotopes and compare them to the kinds of oxygen isotopes you see in terrestrial rocks or in moon rocks or in Martian meteorites and so on. And you find out where things lie in the solar system for oxygen isotopes. But we find these grains, and in this case, this is a map showing this little red dot. That's a grain that has oxygen isotopes that are so wildly non-solar system that we know this was not formed here. This is not a local beast here. And in fact, we can tell based on its isotopes that it probably formed in the outflow of a giant red giant star that predated our own solar system. So these are particles that are older than our solar system. They were made in the outflow of a star, they floated through space for who knows how long, ended up in a dense cloud, and then ended up being incorporated into our solar system. where they ended up in our comet, and then they ended up in our collector. Same thing for the organics. I just already showed this picture that some of the organics show isotopic anomalies that tell you that they probably predate the planets. So these are things that survived from outside our solar system. And again, I don't get too freaked out about this, but we did find organics in the samples, and they are quite complex. We see all kinds of things, some of which are potentially of exobiological interest. One of the things I really want to point out is that little yellow square in the lower left there. That plot shows the ratios of oxygen to carbon and nitrogen to carbon of various extraterrestrial materials. Normal meteorites fall way down in that lower left corner. But things that we think are more primitive, that are likely less processed and therefore more representative of the early solar system, they fall in that slightly higher blue box. But the things we were finding in Stardust are in the yellow box, so they're even way beyond the meteorites. So this suggests that the materials we have really are very primitive, have not been altered by a lot of things. One of the things we found in the return samples is the amino acid glycine. So we know that the comet actually does contain molecules that are now currently used in terrestrial biochemistry. Whoops, I'm just a little too fast. And unfortunately, we also know that we're not going to learn everything we might about comets and their organics because since organics are fragile, even if the comet didn't wreck them, sometimes we wrecked them when we collected the sample. So again, even though we're going into aerogel and that's less stressful than hitting a metal plate, it's still stressful. And so these images in the lower left show you two different tracks, one on the right and one on the left, both of which look pretty similar in visible light. But the bottom image is an image taken with infrared light where we can measure the presence of organic compounds. And you can see the one track is surrounded by a halo of organics, and the other doesn't show any. So this tells us some grains didn't have much carbon in them, and other grains had carbon that we have yet to really analyze because when the particle hit the aerogel, that carbon vaporized and shot into the aerogel and was basically lost to us to do any kind of detailed analysis on. So we know it's there, but we don't know how much it was altered by this process. So unfortunately, here's a case where the sample return isn't going to give us one piece of information we really would have loved to have, and that is what is the ratio of mineral grains to total organics, because we know the organics were selectively destroyed. Okay, and then just another isotopic anomaly. I don't know how many of you know hydrogen is a proton with an electron around it, but there's heavy hydrogen that has an extra neutron. The Earth has a slightly elevated D/H ratio compared to the Sun, but we found that the comet has an elevated ratio compared to both of those. So again, that tells us the organics are not contaminants. They were made in space somewhere, and probably in either the very early cold areas of the protosolar nebula, or maybe even in the interstellar molecular cloud that preceded all of that. So in the end, it turns out that the comet did a great job of preserving materials that were probably made all throughout the nebula, from the very close into the sun to very far out, as well as grains that predated that solar nebula because they were made in the dense molecular cloud where the star formation region we formed from was, or were actually made in other stars and shot out a long time ago and then ultimately ended up in our solar nebula. So we went and got one sample, but we brought back stuff from hundreds of places. And so that made this really interesting samples to look at and are teaching us a lot about a wide variety of different astrophysical environments and timescales. Okay, so what does this all mean? I'm going to try to just give a sort of a highlights reel here for the mission. So the fact that we see this incredibly close association of all these unequilibrated phases, all these things that could not have been made in the same place and could not have been made at the same time, implies that there was a whole lot of mixing going on in the early solar system, that we were getting material from everywhere that was getting out to where the comet formed. But the fact that all of these phases survived without interacting with each other tells us that once they were incorporated into the comet, they were not significantly heated, or they didn't get wet, they didn't get altered in any way. So the comet did a great job of preserving the pristine nature of the raw stuff from which our solar system was made. And not only that, but it even preserved things that existed before we made the solar system. So this was great. And I think that's pretty much it, except I do want to end with a shameless advertisement. It was already mentioned, but the next lecture in this series is, which I believe is next month, is for the OSIRIS-REx mission. I've given the acronym here on the right, and there's a rotating model of the asteroid we visited, and you can see the return capsule, which we got back from that mission in the middle picture on the bottom, based on basically the Stardust capsule design. And then on the far right is a picture of me and your next month's speaker, Dante Loretta's, standing on the right there. And you won't want to miss that talk, because I can tell you that the Bennu samples are amazing in their own right. But I'm not going to give anything away because I don't want to steal Dante's thunder. So sorry, you'll have to come back next month. And that's it. I am happy to take questions then.
All right, well, thank you, Scott, for a fantastic talk. I want to start with a question of my own, which is my prerogative as host, of course. I think a lot of our visitors might want to know, where do comets actually come from? You gave us a great story about how this comet became available, basically, for you to send a spacecraft to encounter it and bring things back. But where did it start? Where do they come from?
Well, that's a great question, and in fact, probably it's not one where. If you look at the distribution of comets in the solar system, it's clear that there's a halo of comets that are in almost a sphere around the sun, way far out in the Oort cloud. But then there's also something called the Kuiper belt, which is closer in and more of a disk. And both of these contain ice-rich bodies that we would call comets if they came in. And so it's not entirely clear whether these formed in radically different ways or whether they were simply redistributed when the solar system was forming, and some ended up in one place and some ended up in the other. But certainly astronomers will tell you that when they measure the gases coming off comets that are coming in or whatever, that it's a real zoo. I mean, you can't just predict when you see a comet what you're going to get out of it when it's warming up. And so they probably formed all over the place. And since we saw that, since the Stardust samples tell us that the nebula was mixing, that mixing probably proceeded on different length scales and time scales at different points during the whole process. And so you could have ended up with comets that have different compositions or formed in different places because they formed at a different time and the mixing was bringing different things in. So I think there's a strong argument. If someone ever wants to send a mission to another comet, there'll probably be somebody who'll say, like, "Oh, you want to go comet? You already been to a comet." Well, we already know very well that not all comets are alike. Going to another comet will almost certainly teach you new things because they are clearly not all alike.
Mm-hmm. I want to remind our audience that we will be taking questions from the audience. So there is a microphone in the back that you can walk to if you have a question. And I can't see you from here because of the lights, but I will be told that you're there with a question. And until someone does get to the microphone, I have some questions here that have come in from folks who are watching online. So one question we have here is, how long did it take to develop the Stardust mission before you got it to launch? How many years of work went into that?
Well, quite a few. It's a pretty standard thing for most missions to, for a team to get together and propose a mission to NASA, submit the proposal, but not be selected. And that's not uncommon because these missions are complicated and it takes a long time to mature all your concepts. Sometimes technology isn't quite ready for you. And so it's not uncommon to propose but not be selected, but then you propose again the next time around and the mission is better. You have the reviewers' comments, you've developed things better, and so on. So actually Stardust was originally based on a mission called Soccer, which was intended to go out in the solar system and collect interstellar dust coming in from outside the solar system, not go to a comet. and that was not selected. But then later we realized that we could do that and visit a comet, and so we wrote the Stardust proposal to do both, and that was a much easier sell. And so there's often many years of lead time while you're developing the plan. Then there's several years where you're proposing and getting your reviews. And then if you're fortunate enough to be selected, then it takes you a number of years to build all the hardware, get yourself ready to launch. And then in the case of sample return missions, they have a tendency to be on the long side because you have to not only get there, but you then have to get back. A lot of missions have to get there and take data, and then they can turn off if they want. And so this makes sample return missions usually quite long. And so I don't remember the exact year when we first breathed the word Stardust, but it was in the 1990s, okay, and then we got back in 2006. And that was with a comet that Jupiter had already half delivered to us, okay? If we wanted to go to a comet that's actually further out, the mission would be, commensurately longer.
I'm told that we have a couple of people at the microphone. Why don't you introduce yourself and ask your question?
Hi, yes, my name's Ethan. I live in the area. It's my first time coming to one of these. Hopefully I do this pretty well. So I guess my question is kind of around like comparative analysis. So I know we have, like Martian rocks, we have, the moon rocks, for example. So when we get these kind of new ones from the comets, does what we learn from there kind of then kind of back inform us maybe on like, oh, now that we know this about the comet, when we go back to look at like the moon sample, we kind of maybe unlock some new mysteries there. Does that kind of happen, or?
Well, there's certainly some of that, and then actually one of the most important things is that anybody who's studying a sample is often developing new and better analytical techniques, and then once they develop them for whatever sample they're looking at, they're suddenly available to all the other folks. And so a lot of the times, people can go back to the same samples they already measured, but now they can do use a new technique or a more sensitive technique, and they can learn additional things. Now, how much of the information you learn from the samples that crosstalks depends a lot on the sample. So, for example, we've got meteorites from Mars. We don't have Mars return from Mars, but we do have meteorites from Mars. I helped find one of them in Antarctica in 1984. Those can tell you a lot about the processes, planetary processes of the history of Mars. But since those processes involve volcanism and weathering and everything else, they're not telling you much about the early solar system materials from which Mars was originally made. And so comet samples and Mars samples are enough at the opposite ends of that spectrum that they don't inform each other a whole lot. You can still learn some stuff, and like I say, the analytical techniques can still crosstalk. So anybody who's interested in one extraterrestrial material is generally interested in almost all other extraterrestrial materials. But the crosstalk for comets is probably the closest would be with asteroids, because this is another type of small body that has, in general, at least for many of the asteroids, not been as severe as for planets. And so meteorites will still show some of these primordial signatures that the comet dust is showing. And so there's a lot of crosstalk between those two. Whereas lunar and Martian ones might have crosstalk when it comes to things like volcanism. Okay, so kind of depends on the sample, but definitely every sample does give you some information about how to interpret and/or analyze other samples.
Awesome, thank you.
We have another question from our online audience asking about contamination.
Yes.
So we know that you used clean rooms to make sure that the samples didn't get contaminated by things that might be on Earth that could then confuse analysis. But was there any concern at all that something would be brought back that might contaminate Earth, maybe something biological?
Oh, yeah, so you're asking a slightly different question than I thought you were going to ask. Let me answer the question I want to answer first.
Okay, yeah, go for it.
Yes, we worry about contamination all the time, because when we bring a sample back from a comet, the last thing we want to do is write a paper where we say comets contain blah, 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 and then we find out it's auto exhaust that got into the system. Okay, so we spend a huge amount of time trying to make sure that everything we do is clean, keep all contaminants out, and try to keep all contaminants out. You can't do it, it's impossible, but you can try to characterize the ones you do have so you recognize them when you see them, and you can try to keep them as simple as possible so they're the least likely to confuse you. Okay, now let's get on to what I think the question they were really asking, which is, were we worried that we were going to bring back the Andromeda strain, okay, yes, and kill us all? And so, no, not really. So NASA, not from Wild-2. So NASA, has a planetary protection officer. They're worried about this sort of thing, but the worry depends on the nature of the object you're bringing back. So if you're bringing back a sample from Mars, this is a valid concern because you think Mars may have had life, and so there could be life to bring back, okay? But nobody thinks that comets and asteroids had life on them. They're simply not viable habitats for anything. And so those are in a different class where they're more concerned about not dropping it on anybody's head as a hazard than they are about bringing back, some weird space virus or a monster that's crept into the cracks. So since I mostly work on small bodies, asteroids and comets for sample return, at least all the missions I've done so far are that, this has not been a major concern. NASA always reviews it. I mean, they always look at every sample return mission and ask this question to make sure that nothing escapes them. But in the objects I've been involved with sample return from, this is not an issue. However, planetary bodies is a bigger concern.
I know we have a couple more questions at the microphone. Would the next person introduce themselves and ask them a question?
Sure, thank you. My name is Shenshi. First time attending one of these things, but really, really appreciated your talk and comments. The question I had was, you mentioned, y'all were surprised that the comet just had such a mixture of different things. And I was wondering if you guys had any insight in terms of how that wasn't disrupted in the formation of the comet.
Well, probably the formation of the comet, it had to be a reasonably gentle process because we know the comet accumulated ices, and so ices aren't very tough. They can't run into each other at high velocities and survive. So this suggests that the aggregation of comets was a fairly gentle process, and that's easier to do in the outer solar system where orbital velocities around the sun are much lower, and so you have less, less velocity between impacting components. And so so it's the fact that all comets are comets because they have volatiles and can eject dust and give tails and things, suggests that they must have accumulated, in at least the ones that survived, in fairly benign conditions. And so that clearly happened with Stardust. If the various components of Wild-2 had been slamming into each other at high velocities, then these things would have been altered by just impact physics. And we don't see that, so or at least not in the collected sample. Who knows? In the middle of Wild-2, for all we know, there's a lump of something that got really cooked. But I doubt it. But it's possible. And so this is one of the reasons why we think the comet itself, even though it has components from throughout the whole solar nebula, probably assembled far out. Because if it tried to assemble in close, everything would have been getting hot anyways. But then also it would have been running into each other at a lot faster, higher velocities, and that this would have caused more damage. So so we think, wherever they formed, or wherevers they formed, things would have been a little more sedate than in the inner solar system.
Awesome, thanks. And I think you have one more question up here.
Yeah, why don't we take the other question from the microphone?
Hi, I'm Katie. I was wondering how you guys developed the size of it and whether you felt that size was appropriate, because it seems like in this new mission you maintained that size and didn't choose to go bigger or smaller. So how did you guys know that maybe that size of aerogel kind of spacing was appropriate for the mission?
It's a good question. Actually, a huge, I talked about how you spend years getting ready to propose, and one of the discussions types that you return to all the time is basically a balance between what's the most science we can get with the engineering available and with the money and mass available. So every kilogram you send into space costs you money, and so you already know based on your budget you can't just send up, a bigger collector would have been great. We would have gotten more stuff. But a bigger collector would have had to fit in a bigger SRC, and a bigger SRC would have been way more complicated and expensive to implement, and we would have busted the budget in a heartbeat. And so a lot of the development of a mission like this is a kind of interesting dynamic tension / collaboration between engineers and scientists. So, I'm fond of saying that, if you only let scientists design spacecraft, they'd never actually take off because they'd always be bolting another instrument on and it would get too heavy to get off the pad, okay? But if you only had let engineers do it, they'd launch a bowling ball and call it success. So you got to find a place in between there where you can make it all work. The scientists feel it's meaningful. The engineers believe they can do it, and you can fit it all within the budget. And I'd say it's really hard work, but for me, one of the more satisfying things is to go through that process, because the engineers and the scientists have to find a common language in the middle so that they are sure they're talking about the same thing. Like, this is a real issue for the whole contamination control thing. Engineers will say, yeah, that's clean because we define clean that if I put my eyes 6 inches from it and shine a flashlight on it, I don't see anything, okay? And a scientist says, that's not clean. You could have a layer of oil on there and we'd have more organic contamination than this total sample we're bringing back. So you have to find the same language, make sure you're all on the same page, and then work together to make it work. So yeah, so I would have loved I would have loved everything on Stardust to be bigger, but there was no way we could afford that.
I'm going to kind of combine a couple of questions that are here from the online audience and ask you, what could be next? Are there any other really good candidate comets out there that you could send a mission to that are the same type of sort of sweet opportunities that Wild-2 presented?
Well, there is a whole family of comets that are called the Jupiter family comets, and it's because they've all had an encounter with Jupiter and they're in these orbits. So there's a bunch of orbits that are somewhat convenient. And so if you try to do, I was a PI on another sample return mission concept we pitched to go down and land on a comet and get a sample. And you find out that there's a cast of characters that keep showing up depending on which launch date you have. You have 4 or 5 candidates that are all kind of in a Wild-2-like orbit you could get to. But they're all Jupiter family comets. If you want to try a further out comet, then that gets a lot more complicated because you have to go way further out in the solar system, and that takes way more energy. But since we know different comets have different histories, and they do seem to be different when astronomers look at them, any one of these other comets would probably be extremely interesting to visit. Some people would like to go back and visit the one the Europeans visited and they hung around with for a long time and watched but didn't bring a sample back. And some people think it'd be great to go there, and now that we know so much about that from the observations, bring a sample back from that. I don't know if you want to go to asteroids. There's many kinds of asteroids out there, and we've only been to, only brought back samples from 2 kinds. So there's a lot of different asteroids that would be great to bring a sample back. I wouldn't mind going to SA Sandford, whatever they showed up there. But unfortunately, that one's way out in the outer asteroid belt, so I don't think that's going to be practical. Also, it's a pretty big object, so it would be a little harder to sample, I think. But we have way more targets than we'll ever be able to afford. And so this is part of the dynamic for the scientists, is to have discussions about, okay, if we know we've only got so many shots in a given amount of time, what's the best way to spend our time to try to get the optimal samples?
We have another question in the audience, and I think it might be the last question we have time for.
Hi, my name is Yaswans, and I'm just curious. So you've captured a lot of the mineral samples coming from the tail, but there's also more volatile material like gas and ice that would be in the tail. So I was curious if you found any traces of that in your sample, and what we might learn from that more volatile material relative to the mineral.
Well, most of the ice, so the ice actually sublimes pretty quickly. If any of it's ejected from the nucleus, it sublimes very quickly. And on these size scales, it's gone in minutes to hours. And so we didn't collect any of that. One of the things we were curious we would see is it was possible we could have seen some tracks and that at the end of them there was nothing, and that would have been like an ice grain that hit the aerogel and just completely vaporized. And we didn't see any of those, but I wasn't entirely surprised because grains on that size scale made of ice really wouldn't have survived in a vacuum for very long. So we don't have any strong evidence of that. On the other hand, the glycine detection we got was not, the glycine wasn't found in an individual particle at the end of the track. It was found in material coating the side of one of the aerogel cubes, as if it had arrived as a gas. And so whether that means it was in a particle and got vaporized out and redeposited, or whether it actually was arriving as a gas, which might have once been an ice, and the aerogel managed to pick up a little of that, well, I don't think we really know. But we do know the glycine is not just a contaminant because it has non-terrestrial isotopic ratios. It's clearly from space. So, this is one of the reasons why NASA would like to do a surface comet sample return, is that this gives you a better chance to go down and actually probe the ice, because the ice should still be in the comet's surface at some depth, whereas all the stuff we were collecting had been, had already traveled 236 kilometers out from the nucleus, and so most of the ice would have just turned into gas.
All right, well, that is all the time we have for tonight's talk. I want to thank Dr. Sandford again. Please help me thank him with a great round of applause.
My pleasure.
And I'd like to announce a few things, which is, first of all, tonight as you leave, across the street from the museum, some of our astronomy educators are going to be facilitating stargazing over at the Eisenhower Memorial. So if you're interested in looking at the stars tonight, join them. Our next Exploring Space lecture will be on May 22nd, when we will have Dante Loretta talking about OSIRIS-REx, revealing secrets from the dawn of our solar system. And if you're a National Air and Space Society member, or you want to become a National Air and Space Society member, you can visit the Udvar Hazy Center next Friday, May 3rd, where I'll be in conversation with author Andy Weir, who's going to be commemorating the 10th anniversary with us of The Martian. And finally, thank you to our sponsors, Aerojet Rocketdyne and United Launch Alliance. We're grateful for their support for the Exploring Space Lecture Series, and we're also very thankful to all of you who came out or who watched online tonight. Thank you very much.
And go look at the capsule if you haven't already.
Yes.